He did his studies, the first 3 years of his studies in Karlsruhe, and then he moved to Edinburgh in Scotland, did his master in physics and optoelectronics and lasers there, and also stayed for his PhD. He's been working with Richard Warburton there on spectroscopy of single quantum dots, and that's also what he's going to tell us about today. It's quite spectacular work, as I think. He has already been able to publish one Nature and one Science with the results, so I'm very much looking forward to your presentation.
Well, thanks for the introduction. And yeah, today I'm going to talk about coherent spectroscopy on single quantum dots. And so this is the group I've been the last 4 years with, and all the samples we were using are coming from the University of California in Santa Barbara and Pierre Pedro's group. And of course, thank you for the opportunity. So, okay, the motivation, why do you want to study single quantum dots? Well, the first is it's a good gain medium for lasers, but at least from my point of view, that's more of an engineering task, maybe. But what I was more into, and what was my PhD was about, was the atom-like behavior of single quantum dots and their realization in a solid-state environment. And some practical advantages of such a system is that you have an atom-like system which you can scale and control much easier than you can do it with atomic vapor. The other thing is that using single quantum dots, you can study quantum mechanics on a single wave function level, so you can do spectroscopy with one wave function and one wave function only, so it's not an ensemble measurement. And the other thing is that quantum dots for quite a while have been considered promising candidates for quantum information processing, like for example here a qubit, where you exchange the classical 1 and 0 presentation from a binary system into the coherent superposition of two quantum states. So the quantum dots I studied were self-assembled quantum dots, semiconductor material. And for that, you have a gallium arsenide substrate, and you use molecular beam epitaxy to basically put a vapor of source materials on top of that. And now the evaporation sources in our experiments were indium arsenide. So if you now grow a layer of indium arsenide on top of a gallium arsenide, the lattice mismatch between the atoms of the two different materials lead to strain. It's a bit like if you look at a frying pan of Teflon and you put water on it, you see these little droplets forming. So it's a similar effect to that. And if you go above the critical thickness of such a layer, you have these single or small droplets forming on top of the gallium arsenide. So the ones you want is in this area. If you go to big quantum dots, then you have dislocations. And finally, you will end up with something like this. So this is an AFM picture from basically this plane. So you see all these single dots here are single quantum dots, and well, they're pretty regular in size and shape. Now the next image is basically a cross-section through a single quantum dot, and you see here the material here corresponding to the bright part is indium arsenide, while it's completely surrounded by gallium arsenide. So that means first you have a self-assembly process, so you don't actually have to worry about anything but the thickness control of these layers. And the other thing is that you have a 20 nanometer, more or less, sized island of indium arsenide surrounded by gallium arsenide. So the interesting bit now is if you look at the band gap energies of gallium arsenide, you have 1.42 electron volts, but for indium arsenide you have 0.35. And what that means is that you actually have a potential trap, a potential well in all three dimensions for electrons as well as holes. So that here is the conduction band, and here you have the valence band. So in the position of the high concentration of indium arsenide, you have a potential minimum for electrons as well as holes. So that means that you can find them in all three dimensions on the size scale, which is comparable to the de Broglie wavelength. And then you have this quantized system.
Can you mention what you say in the dimensions, but in the vertical?
In all three, well, this size is roughly 20 nanometers.
So when you mean 3 dimension, you mean that it's confined both in the surface, of course?
Yeah.
But then in the vertical, it's confined with air or something?
No, it's completely surrounded by gallium arsenide.
So it's within the gallium arsenide?
It's basically you have one indium arsenide droplet and it's completely surrounded by gallium
I thought
arsenide.
it was on top of it.
No. I mean, you have a spatial asymmetry, but in the end, it's all surrounded by gallium arsenide. So one important aspect that you have a potential minimum for holes and electrons is that you can confine something which is called an exciton. So you can excite an electron state from the valence band into the conduction band, which then leaves the hole behind. That's that void of an electron in the valence band is called a hole in semiconductor physics, and then you have this combined particle which is called an exciton. Another analogy to the atoms, you can basically have this shell model which applies to atoms, but also to quantum dots. So in indium arsenide quantum dots, you have basically these 3 shells or 2 shells, and these 6 states for the conduction and for the valence band. Okay, so what do you now do with such an atom-like system in the solid state? Well, you can do what you do so well with semiconductor material science. You grow some functional structure around it. So if we start from the bottom, this is the gallium arsenide substrate I was showing you before, where you grow the indium gallium arsenide on top of it. The next step is to grow a highly doped region, which can be negatively or positively doped. You cap that again with gallium arsenide, then you grow the indium arsenide quantum dots on that with another capping layer of gallium arsenide, and then you cause something like it's called a superlattice, which is the electronic equivalent of a Bragg mirror, basically. So on top of that, you do gallium arsenide, and then we have a semi-transparent metal top gate. What you can do now is you put an indium material here, you heat it up, and then this diffuses down here into the highly doped region. And that means you have now an electrical contact from the top to the bottom here. And since this area or this structure forbids electrons to propagate from the top to the bottom or any carriers, this means you have a capacitor here, so you can apply a voltage between the top of the structure and the bottom of the structure. And this is good for 2 things. The first is that you can use that to selectively charge a quantum dot. So here you have the highly doped region of the back contact, which is the equivalent of this. So you have to imagine the structure basically physically going along this line. So you have the free carriers in the back contact with the Fermi energy. And now by applying voltage between back contact and Schottky gate, you can change the tilting of this band. And thereby you can change the potential energy of the quantum dot relative to the Fermi energy of the back contact. And that means if you're at resonance from back contact and the Fermi energy, you will get tunneling of one carrier into the quantum dot. And you can now play this game, you can lower or raise the voltage, and thereby you tunnel in or you tunnel out. The next benefit of this structure is that you can use the DC Stark shift, and with that you can tune the energy of a single exciton in the quantum dot, which is quite important later on. So how do we now examine these structures? This is basically only the microscope system I'm showing you. This is all connected to a whole lab full of other devices, but they're only relevant for the measurement process. So here we have something we always call the microscope head. So here we have optical fibers coming on horizontally and vertically. Usually this is excitation fiber. Here's some polarization control, which is deviated down here. And then you can have either a second source going down this propagation path, or you can also use this one, for example, to collect emission or to do other types of spectroscopy. The CCD camera is only used for imaging what happens down here. So we then take this microscope head on top of this microscope tube. This in the real world is about 1.5 meters long. Down here you have small piezo motors which you can position control the quantum dot sample to, I think, a couple of nanometers accuracy. And on top of that sits a detector, the quantum dot sample, and the cell, but I will show another picture of that later. And then all of this basically goes inside of this liquid helium triostat. And this modular design is basically used to optimize all single components while still providing high stability. So we managed to observe a single quantum dot, which is all the way down here, and for 20 nanometer sized object for 10 weeks, I think was the longest time now, with refilling helium and everything else. Okay, so how now do we use all this structure in the experimental setup? Well, so here again we see the band structure of the device for different gate biases, gate voltages. So for the first one, the ground state of the valence band minimum is in contact here with a p-lobe back contact. That means that that'll be occupied by one hole. If we now excite the exciton with a higher energy laser, this exciton will provide one electron which relaxes into the quantum dot and can then, this is usually with phonon interaction, and this can now relax and recombine with the hole in the valence band. And if you look at the spectroscopy now, this is luminescent spectroscopy, so we use the microscope system to collect the emission of the quantum dot, we use some filters to block out the excitation laser, and then we change the gate bias. So we now look for this one here, this state is X0 emission, this would be here, and now all we have to do is tune the gate bias to a different voltage, and then you jump to this other quantum state where you have the second level of the valence band in resonance with the Fermi energy, and then you get an additional carrier, and that's the next quantum state inside the quantum dot. So you can use these structures to really deterministic charging of single quantum dots, and I think the record was from +8. So this is basically excess of holes, and this is excess of electrons, the plus and minus, and I think the
only one quantum dot.
Yeah, that is single quantum dot spectroscopy, all of it basically.
This is because you only have one in the wafer.
No, you have millions in the wafer, but you grow them with the density profile, so the density goes from high to very low, and then you just drop out the region that density is very low, and then you can move the sample around, and you see a region. I mean, maybe, this is from 957 nanometers to 964, so maybe there's another one all the way up here, but you can isolate them spectrally. But you can also make the density so low that you only find one. So, yes, but all I'm showing is single quantum dot spectroscopy. Where was I? Yeah, the record charging shown so far, I think, was from +7 to -8 or something. So it's really a very versatile structure. So, but this is all non-resonant because you excite with high energy, and you have to have a relaxation process in here. So you cannot really coherently transmit information optically from outside the system to a quantum state, because you will lose a large amount of information in exactly that process. So the next step is to do resonance spectroscopy. And for that, we use a narrow line with laser, which is the line is much narrower than the transition line of the exciton state in the quantum dot. And for example, we now leave the energy of the excitation laser constant, and we tune the exciton using this DC Stark effect I was showing before. And now we have these two situations. When you're off resonance, the laser will just transmit the material, because there's, besides the quantum dot, there are no states excite inside the sample. But if the laser is on resonance, the exciton will start to oscillate in the electric field of the laser, and thereby it's basically an oscillating dipole. And then it scatters a fraction of this field, and what we now do is we detect the homodyne field of laser and oscillating quantum dot, and then you get something like this. So this now is basically the transmission spectrum of an X0 of the quantum dot at some gate bias, and then if you now go to a different voltage again, this is the X1 plus. So there's two holes and one electron is the excited state. So these are the two states we can easily access in a positively doped sample. Here you see the fine structure of the neutral exciton that is due to spatial asymmetry of quantum dots, but yeah, that's just a general feature which you can also use to distinguish between X1 plus and X0. You see the line widths here, they're all in electron volts, so 4.3 microelectron volt. If they would be lifetime limited, they should be around 1. So you can already see that there are some processes going on which are not quite pinned down yet. And okay, exactly. So what is the big appeal of this resonance spectroscopy other than just measuring the real line shape, because your resolution is much higher? Well, if you look at the quantum mechanical system, this is just a 2-level system. Here you have the coupling laser omega L, that is the interaction strength between laser and transition. And down here you have the density matrix, or the Hamiltonian, which represents such a system. And the interesting bit is now this leads to an evolution of the overall state vector of the system, which goes from, let's say, if you start at time 0 with all the population in the ground state 1, you basically start to oscillate between these two states if you have a high intensity excitation laser. And these are the so-called Rabi oscillations. So that's probability of being in state 2 and in state 1. But actually it's much more than that, because it's a coherent superposition of state vector of the ground state and because of the state vector of the excited state. So it's not just counting populations between two states, but it's really creating basically a coherent superposition, like interference in an optical field. So this is a small animation I found on the internet. So this shows the transition between a 1s and a 2p state of I think helium. I don't remember. But anyway, you see that now you're in the ground state, and now you drive the oscillation more and more, and you start to get superposition between the 2p and the 1s state. So it's not just projecting in one or the other state with probabilities, but it's actually creating a superposition of both quantum states. And that is the real benefit of this resonant coherent excitation.
So what are the axes of the picture?
I don't know. I think that's spatial dimensions. This is not. This is just to visualize the. It's not anything I've done or measured or something. It's just a nice picture from.
Sorry, at the beginning you said that you were using such plugins also because they have only one wave function. In the plots you are showing the S level and E level. So you are using now 2 levels. So is this a limitation, or using 2 levels, or you can build with any number of levels, or is number? I mean, you can choose the material to use only 2 levels.
I mean, how many levels you can confine it depends on the first the bandgap of both materials, and then how the size of the quantum dots. So if you make it bigger, the level spacing gets smaller, then you can fit the D shells in the quantum dot as well, for example. So there's certain engineering freedom there.
So the question is, so are you restricting to be in the 2-level system because of what we call simplicity?
No. So I will show experiments with the 3-level lambda system later. So it's the 2 levels just to visualize it more easily, because I don't know how a 3-level system looks like in the quantum state. That's just to visualize it. Okay. Right. So how do we go from this resonant experiment now to the quantum mechanics, which happen inside the quantum dot, or the interpretation of that? So here again we see the 2-level system, just for simplicity. Then we have a relaxation process from the excited state, and something I haven't shown here, but a dephasing of the second state to the first state. That means if the system would be entirely in state 2, in this dephasing time, you would not move population from the second state into the first state, but it would just lose phase, like an optical phenomenon. That just the coherence length of a laser, for example. Now to model the system, we use something called the density matrix approach. So here you have density matrix, and here you have the Hamiltonian of the system, and it's commutated with the density matrix, and that gives you the coherent dynamics in your system. But now you also need some mechanism to include relaxation mechanisms, like, for example, relaxation from the second state into the first one, or the dephasing of the second state. And this is in the so-called Lindblad equation here. And for a two-level system, we can now do some maths, and then we basically end up with this representation. And because we don't do pulse experiments, but always continuous wave experiments, we always look at the steady-state solution of the system. And therefore, basically, this absorption contrast I've shown you of the resonant laser is then for two-level system given by this standard Lorentzian equation, where you have the relaxation. Here, gamma 22 is the dephasing rate, and also you have a term with power broadening if you use an intense laser. And pardon?
What is delta?
Delta is the tuning between laser and the resonance. And basically, the important message is here is that we can really use this resonance spectroscopy to get access to the quantum mechanical information of the system. So yeah, it's really it's quite an essential tool. Okay, now my first was a summary of the experiments. The first thing I'm going to show is seeing a whole spin initialisation. So that is basically dictating the system what quantum state I want to be in. And we use holes because everyone has looked at electrons before already, and we think holes are better. The next one is resonance fluorescence. That is an experiment where you create a quantum state resonantly and you collect the emission of that, which is quite challenging experimentally because you cannot filter it. It's exactly the same wavelength. So the quantum dot and laser photons are degenerate in energy. And the last experiment then is creating a coherent superposition of two different states inside the quantum dot. And again, we use Hall spins for similar reasons why we use them for the initialization. And somehow this represents a roadmap to this whole topic of quantum information processing, because first you need to initialize a state, then you need to be able to read it out, and the next step is to create a coherent position. Okay, so to optically initialize a Hall spin, what you need for that is first is long relaxation rates, because you want to have the Hall spin stay in your intended state as long as possible. The next one is we want to do that all optically, so we need to have a scheme which allows us to optically manipulate the Hall spin of the spin up or spin down. And the other one is we need clean selection, optical selection rules for this, because if you cannot really address one state directly or unambitiously, then well, clearly or clean enough, then yeah, the whole experiment will be mixed up with. Okay, so what is against us? So if you look at the quantum dot, it consists of basically relaxation. What kinds of relaxation mechanisms are there for carrier spins inside the quantum dot? So the first one is the interaction between the single carrier wave function and all these tens of thousands nuclei the quantum dot actually consists of. And because we are in a 3-5 material, all these atoms of the host material, they have a nuclei spin. And they, of course, can couple to the spin of the carrier trapped inside this quantum dot. And you can now have interaction on the single atom level, or you can have interaction of the overall field, because tens of thousands atoms here is pretty unfortunate, because if it would be millions, then you wouldn't have a preferred direction of the magnetic field, because it would just average out. But they're too much to really control each one of them individually. So if you just look at the magnetic dipole-dipole coupling between a nuclei spin and the spin of a carrier inside this quantum dot, you can write down these, you can split it up in these three terms. Forget about these terms. The important part is that here, the first term is you have a delta function. So the coupling between carrier spin and the nuclei spin here is only exactly at the position of each quantum dot nuclei. The next term here is again a nuclei a carrier spin coupling, but here you have these normalized direction vectors. So in the end, what this results in is it has a orientational dependency. So this term will depend on the actual symmetry of the wave function. And the next term here is just spin-orbit coupling. So this is one big chunk of interactions. The other one is due to the highly doped region we have inside the sample and in tiny contact to the quantum dots. So again here, if we have a big energy tuning between quantum dot state and the Fermi energy of this, due to the Fermi distribution and the energy conservation of the tunneling process, there will be no or very little interaction between these states here in the highly doped region and the quantum dot state. But however, if we raise this energy and are in resonance, then there will be a fast exchange between the state in the quantum dot and the state in the back contact. And because states in the back contact are not polarized in any means, this will quickly randomize the state we have inside the quantum dot. So this will show, this will have a big influence, and also the thing here is it will have a dependency on the applied voltage. Okay, so now to show you why we think holes are a bit, or at least interesting and a bit more promising maybe than electrons, is you can even look at the Bloch wave function. So a carrier confined to a quantum dot has an overall symmetry which is dictated by the shape of the quantum dots. So we assume parabolic confinement potential for quantum dots. And this has been fitted by experiments, and it agrees more or less, at least for the lower states in quantum dots. And then you have the symmetry which is called the Bloch wave function, which is dictated by the nuclei or by the atoms the quantum dot consists of. So now here we have a hole, and because a hole is a valence band particle, the valence band in gallium arsenide or in indium arsenide consists of p orbitals. So that means you have this p symmetry, which has goes to zero at, or the probability density goes to zero at the position of each nuclei of the host material. However, if you look at the electrons, they have an asymmetry because they're conduction band. And that means the maximum probability is exactly at the position of the nuclei. And this now has a big influence on the nuclei spin coupling. So the first is for holes, because we have a zero at the position of the nuclei. The first interaction term, this delta term, is zero. But because we have this spatial asymmetry, H2 is not zero. And because it's a p state with L plus or minus, we have spin-orbit coupling. With electron, however, you have the maximum probability at the position of the nuclei. That means the first term is not zero, but the second term and the third term is zero, because first it's a S state, so it doesn't have any spatial dependency or orientation dependency. And you don't have orbital momentum, that's why the third term is zero. And this now leads to very different physics between electrons and holes. So how do we do this experiment? Here we have the 4-level system of a hole spin in the quantum dot. So the quantum dot is charged with a single hole. Depending on in a magnetic field, the spin can be up or down, and this energy difference is the Siemens splitting. We can now excite with circular polarized light, sigma plus or sigma minus, and create this exciton here where you have an additional electron-hole pair. And here you now have a spin singlet for the holes and an additional electron spin down or spin up. In this experiment, the magnetic field is applied across or along the growth direction. So we use this scheme now to, for example, excite with the sigma plus laser. You couple these two levers. If we go just in terms of populations, we populate the excited state. The electron spin now, because of the strong contact interaction and because it doesn't have any orientational asymmetry, couples to the nuclei spin and starts to precess in the vertical component of the nuclear magnetic field. And thereby you have a coupling mechanism between electron spin down and electron spin up. And now, due to spontaneous relaxation, you can either relax into that state, where you are just excited again, or you relax into here. And then you're trapped here for the case that you have long relaxation times and that the whole spin doesn't precess in the nuclear field itself. So that's our idea of the system. So as soon as you're here, means because of the optical selection rules, you cannot access the system anymore. So now here the first experiment, we pump only with sigma plus polarized laser, and here we don't see anything. So the interpretation is, okay, we're here and we don't have access. Then we change the polarization, pump with sigma minus, and again the same happens. But I mean, everybody can create a system which doesn't interact. That's just an error in the experiment because you produce such a result. But what we can do now is we pump with both lasers at the same time, and then each laser frustrates the storing mechanism of the other laser. And there suddenly you get this whole interaction back. And that basically is the confirmation that you successfully stored population in that state or in that state, because you can now basically destroy the same mechanism. And one thing is to note here is this is all at zero field. So this addressing is only done by clean optical selection rules, so that already shows that the quantum dot really behaves at least to a high degree like an atom, or like an idealized atom in this case. And because the energies are completely degenerate, there's no energy in selectivity. Okay, so how do we study this effect a bit more? Well, what we can do is we increase the external magnetic field, and what we do now is, well, the overall magnetic field of the nuclei doesn't have any preferred orientation in space or in direction. So let's assume it's 45 degrees. So you have 45 degrees. So that means you always have a big XY component, the electron spin can couple to, and that leads to this electron spin precession. So that means that you have a strong coupling of these excited states and fast population transfer, which you need to populate this state with only this laser. But if you now apply a magnetic field in Z direction, which is parallel to the initialization direction of the electron spin, that means that the effect of the internal magnetic field, which is at 45 degrees, gets less and less important, and thereby the speed or the effectiveness of this coupling mechanism due to the electron spin precession gets less and less important, and you get less and less population from this state into that state, and that makes the system, once it's excited here, relax into that state by a vast majority, and only very seldomly in this state. So if you look at the absorption contrast, at zero external magnetic field, we get very fast post-spin initialization, so we pump, and very quickly we are here, and then the system can't exist anymore. But for example, at 5 Tesla, we have very slow coupling, and we will only very, very, very rarely end up here. So that means most of the time we have just a normal transition here, and that's why we see strong interaction. So here you see the strength of the absorption signal. At 0 Tesla, it's very effective spin pumping. So effective spin pumping means no interaction, and then we have small absorption contrast. And then this comes back, the absorption signal comes back slowly while we basically increase the external magnetic field. And the solid line here is a fit with the 4-level density matrix equation. So that's not some averaging or something. So that's really fitting the quantum dot consisting of tens of thousands atoms with a model intended for one atom. So it really shows how equivalent they are, at least in this experiment. Okay, and the important thing is that we get a whole spin relaxation time. We extract that out of the theory of 1 millisecond, which is for quantum information processing is very, very long. It's a good result. The next graph is we show this dependency on the gate bias, so this tunneling mechanism between the back contact and the quantum dot. So we see here we had resonance of between quantum dot and the back contact. And because we just create this X1 plus state, and here we lose it again, and that means here we have strong spin randomization at this point and this point, and that again means that we get the overall absorption signal back. In the middle now we have this plain line, but it doesn't show any bias dependency, and that's because we have 1.5 Tesla and the electron spin precession is already slow, and thereby we still get a significant amount of absorption. But the dotted line here is a fit of this result with theory describing this tunneling mechanism, and we use this to extract the tunneling speed between the back contact and the quantum dots. And at the two edges here we get 3 microseconds, but in the middle here we get 100 milliseconds. So that means that this process is irrelevant at the middle of this voltage plateau. And that is basically the first experiment characterized. So we extracted the relaxation time, and we have shown that the whole spin doesn't really interact with the nuclear spin. The next step is how do we read out such a resonantly created state. And for that we need strong suppression of the resonant laser, which is quite tricky to get it to a high enough degree, because you need attenuation of 10 to the 7 or something. And then we also want to integrate it into the existing device we use. So for that we just slightly adapt this typical microscope head we were using and introduce some polarization filtering here. So we come from the side for excitation. We collimate this beam with a very small diameter. Then we polarization filter it, rotate its polarization by 90 degrees, and basically let it propagate through the similar polarizing beam splitter as we have here. And that means because of the 90 degrees rotation, it will be deflected downwards. If you now imagine down there the quantum dot sample, it will bounce up again, also the quantum dot photons, but now the laser is collimated to a small diameter, whereas the quantum dot photons will basically fill out this whole lens here. And that means for the first filtering is the polarizing beam splitter, so that will deflect this one again back this path, and thereby will result in an attenuation of 4 times 10 to the minus 6. But then we have a shadow mask over here which blocks the middle part of this beam, and thereby leads to another attenuation of the photons by 3 times 10 to the minus 3. So we should be able to collect photons which are, or the intensity of the collected quantum dot photons should exceed the number of collected laser photons. And there we can now directly go to an experiment. So here we excite the x1 minus state. We use x1 minus for some other reasons. So in principle this is also applicable to Hall spins. So you just excite it with linearly polarized light, and then the relaxation photons will be circular polarized, so sigma plus and sigma minus. And then we will always collect 50% of either one. And here we see a scan. We again have the laser at the constant energy. This is the line of elevated counts here. And then we tune the quantum dot through the resonance, and here the resonant hits, and this basically is the spectra of the collected quantum dot emission. And if you now cut through this, you can see here at the low power you see this spectrum, and at higher power you already see the power broadening. And here we now use this resonance fluorescence to basically validate this technique, because the transmission spectroscopy has been around for a few years now, and it's been taken to be a valid experiment. And here we see that basically the resonance fluorescence perfectly, or almost perfectly, reproduces the features measured in standard resonance transmission spectroscopy. And here again 2 example scans showing the power broadening and the saturation of the transition. So this basically is a proof of principle, not more. We use the same results to calculate a signal-to-noise ratio, which is around 100 for unsaturated transition here. And yeah, this is basically the contrast dependency and the collection of laser photons. What we also did is we were using this device to study the emission statistics of the quantum dot, and we can already see some hints of Rabi oscillations here and an anti-bunching dip in the middle. But the signal-to-noise ratio has to be improved at least by 2 orders of magnitude to really do quantum optical experiments with this setup. But we should be able to at least collect a resonantly excited state. So for quantum information processing, this system is good enough. But to really do quantum optics, like the Molotov drifted or something, we have to improve it by quite a lot. Okay. So now to the last topic, and that's the coherent superposition of quantum dot states, and in our case the Hall spin states. So how do we create a coherent superposition of 2 ground states? So you need a coupling mechanism between both states, which is coherent, so it cannot involve transition to another excited state, as we had in the experiment before, where we had 4 levels, and the excited level is coupled by the electron spin, spin up or spin down. So we need to create something called a lambda system, where you have 1 excited state and 2 ground states, but we will see it very quickly. The other thing is, if you want to measure the decoherence rate of the Hall spin, we need an experiment which is sensitive to the phase of the Hall spin. And that one very prominent experiment here is called coherent population trapping. And coherent population trapping now refers to this lambda system. We have the two ground states, so spin whole spin down and whole spin up, and we couple them to the same common excited state. And this is now basically this lambda mechanism. And because they couple directly between these three without a fourth state involved, this whole process is coherent besides the dephasing of the individual states. If we again look at the Hamiltonian here, we have the three-level Hamiltonian of the system. And now the very interesting part is you can now look at the eigenstates, eigenvectors of this Hamiltonian. And you get these three new three eigenvectors. I've eliminated the prefactors here. They basically depend on detuning and pump intensities and things like this. But the really important part is here that the A0 eigenstate, the new one, doesn't have a probability of the third state. So that means it cannot couple to the optical field. So it's a dark state. While all these other states have contribution of the excited state. So here these states can be coupled optically, but this one cannot. And this now leads to this optical spectra. So here you would see the normal Lorentzian absorption, but in the middle here, suddenly you get a very dramatic and sharp dip, which is called, and here, at this state, at zero detuning from the probe laser, from this transition, you suddenly see zero absorption. And that is, here, that all the population is trapped inside this state and cannot couple to the excited level anymore, and that's why it's called coherent population trapping. So, and now because this state here corresponds to two ground states, and we've shown that whole spins have a very long relaxation time, it is sensitive to the dephasing of the spin states against each other. Because this, in the end, is a superposition of two quantum states, and like with an optical phenomena where you interfere to optical beams, you can only do it in the interference or in the coherence length of the system. Here you can only do it in the coherence timescale of the system. So this, the visibility of this dip strongly depends on the coherence of state 1 or the dephasing of state 2 relative to state 1, let's say. Okay, and from that we can go straight to an experiment. No, exactly. How do we do this experiment? So for this, we apply a magnetic field in XY direction, so perpendicular to the experiment before. Before it was in Z direction, now we apply it in XY direction. And that now changes the optical selection rules, and suddenly you have all these 4 transitions allowed. Before we only had 2 transitions, and now they're linearly X or linearly Y polarized. So that means you can now create 2 different lambda systems. This lambda system here with the coupling both whole spin states to the electron spin down state, or this lambda system coupling both whole spin states to the electron spin up state. But this is only, well, an experimental necessity. The other interesting bit is if you look at the interaction Hamiltonian between nuclei spin and whole spin, or nuclei spin and electron spin, they actually have a very different asymmetry. So this is basically the sum of H1, H2, and H3, these different dipole coupling terms I introduced before. And it can be shown that for holes, this Hamiltonian has a very strong asymmetry in direction, while for electrons it doesn't have. So this only couples the Z components of carrier spin and nuclear spin, while this here couples all components. So that means, the hole only couples to the Z component of the nuclear magnetic field, while the electron couples to all of them. And that means that if you apply a magnetic field in X direction, at least for the holes, you can suppress the remaining interaction very, very strongly. And from that we can go directly to an experiment, and here we see the very, or zoomed in picture, the very broad absorption line of this exciton transition. And in the middle, or almost the middle, we suddenly see this very dramatic and very, very narrow dip all the way down to 0. And that is exactly this quantum interference between whole spin up and whole spin down state we are in this case, which is dark. So the 2 really important messages to take away just from this graph, without doing any further analysis, is that the graph is, or the dip is all the way down to 0. So at least at this coupling intensities of the lasers, at these low coupling intensities, that must mean that the whole spin is very coherent. The other thing is that the exciton line is very, very broad. So this is, I think we measured 8 microeV instead of 1, which would be the lifetime limiting. So something is completely messing up the exciton. But in the end, this doesn't have any influence on the whole spin, because otherwise this line would be very, very broad. So these are the two messages. The dip is very narrow, while the optical transition is broad. That means that the coupling mechanism broadly in the electron in the excited state doesn't affect the whole spin of the ground state. The other thing is that it's deep, so it must be very coherent, much more coherent than the radiative lifetime of 1 nanosecond of this transition. To compare it to some theory, well, this is this classical lambda system and the graph I've shown before. So if you now look at a 1 microsecond coherence time of the ground state, you see this interference, or this dip goes all the way down to 0 because it's very long-lived, and you don't need to initialize it so often. So once you initialize it, you will sit here for a very long time. But if you decrease this to 100 nanosecond, this dip moves up, and it will move up more and more the less coherent the system gets. So that is how you measure the coherence time of these two ground states. The effect of a detuning of pump and probe laser now will be this one, that this dip will move to the side while the maximum resonance will stay at 0 detuning, which is really not what which is not what we actually see. So to adapt our theory, what we did is we broadened this excited state just by convolution with the Lorentzian line here. And then suddenly this overall spectrum changes to this shape. And this is pretty much what we observe in the experiment. So here we are positively detuned, and the maximum is next to the dip instead of in the middle. And we still have this narrow dip, and then well, the normal line 1 is on. Here we have 0 detuning, and here we have negative detuning. So this pretty much corresponds to the textbook Lambda system model. Just what you have to add is this convolution of the excited state. And this is some proof that we really deal with coherent population trapping and not something called outlet horn splitting. So this is the position of this dip here of the dark state plotted against the detuning of the pump laser. And you can see that it basically follows perfectly what we in theory you would expect a slope of 1, and here you basically get slope 1. Okay, so how do we extract the coherence time of this now? So here simulations shown with the coherence time for 1 nanosecond. So this is a blow up of this whole optical transition. So this is only showing the dark state. So the spectrum will go on and then drop to 0 again, as the normal Lorentzian would be brought like this. And here in the middle we see the dip of the dark state. So now by changing the coherence time of the ground state, this dip gets more and more and more pronounced. And you see here, I mean this is just an example, but to really reach the 0 measurement value we got here, we need a coherence time of the ground state of 1 nanosecond. But of course this is an experiment, and I mean this is a very beautiful scan. You have more noise and everything. So what we've done is we averaged, or we measured 10 scans, and we fitted our results to this, and that basically gave us the overall or an estimate of the coherence time of this ground state. So what you can see here is a confidence plot showing how confident you can be that the whole spin will be longer, the whole spin coherence time will be longer than the lower limit we calculated here. So we can now say from our measurement results that the whole spin will be more coherent or coherent for longer than 200 nanoseconds with a 99% certainty. And as you increase this number to half a microsecond, this goes down to 70%, but still with 40% certainty we can say, okay, it's 1 microsecond or longer, which is quite significant. I mean, the electron spin, whatever you do, unless you do something, spin echo techniques or something else, you can never get the coherence time above 40 nanoseconds. So to get around 1 microsecond just by choosing a different system with a different block wave function, I think really shows the fundamental difference of the two quantum mechanical systems, and how this quantum dot actually really gives you access to the quantum mechanical physics which are happening in this material. And this is why I think it's such a nice experiment, because you don't only get the results, but also you can show the fundamental difference of very simple quantum mechanics. Okay, so I think I conclude, and my outlook is, so we succeeded in hosting coupling. That was the first step in the roadmap of this quantum information processing. We extracted a long relaxation time for the host bin states, which is very important, especially also for quantum error corrections. We also succeeded in readout of resonantly created quantum dot states with a signal-to-noise ratio of roughly 100. But most importantly, we could show that host bins are a very coherent system, much the opposite of electron spins, and that really opens a completely new field, because so far pretty much no experiments, at least in single host bins, have been done in semiconductor materials. You either have an ensemble of host bins or nothing else actually. And also the theoretical side of this, it's completely unclear yet what is actually interaction between electrons and holes with the semiconductor environment. So it's really important to get an insight, because all the theory which exists so far is only explains half of the story. So there's still, I mean, even though it's a long studied subject, there's still a lot of knowledge to gain. And this coherent host bin state can now be used also for quantum computing, like the qubit I've shown before. So what you could do is, for example, you grow two quantum dots very close to each other, and then you can shift a state from one quantum dot to the next one by changing voltages, for example. The other thing is this CPT dip we've shown here is much narrower than anything else seen in semiconductor physics so far, at least to my knowledge. So normal line widths here are, I would say, of the order of half a gigahertz in frequency. So the narrowest dip I have measured was only 16 megahertz. So that moves the finesse, let's say, of this dip, or increases it by 3 orders of magnitude. So by, for example, applications in metrology or frequency standards on something like this, you now suddenly have a system for the coming from the solid state environment, which can give you very accurate references. So, thank you.
Thanks a lot, Daniel. Are there questions, comments? Yes, please.
What are the next steps? Will a quantum computer do this?
To what? The quantum dot?
Quantum computer.
I mean,
with quantum dot.
yes. So if I should be completely honest, I don't think you will ever do a quantum computer with this. No way. I mean, the different quantum dots, they are so degenerate, they're so dispersed in energy, it's never going to happen. But there's different schemes to create this. I mean, this is only self-assembled quantum dots, so they are subject to this somewhat random mechanism. But you can also create them lithographically. So you just grow some layer of semiconductor material, and then you apply electrodes on top of it. But because this is based on Coulomb interaction, you can only either confine electrons or holes. And so far, these experiments have not been able to be conducted with hole spins because of noise problems or anything else. So this complete field in semiconductor physics has been ignored for years and years. So, I mean, you can actually use hole spins to then move into a quantum computer in a solid state, but not the surface on the dot state.
But the dephasing time certainly plays a crucial role for.
Yeah, that's.
And just a question to that, because you argued certainly electron spin versus hole spin, And if I have correctly in mind, recently, let's say the Yamamoto and Porsche group have been seeing that also with the electron spins, if you use photon echo techniques, you can get to 3 microseconds or something like that. If you would use echo techniques here, what would be the limit?
Well, that's exactly it. That's a very that's really discussed question, because the spin echo technique only compensates for horizontal dephasing, and because at least the theoretical interpretation is that because the whole spin only comes from the z direction, it will not feel anything of this vertical dephasing. So at least if the theory which is out there at the moment is correct, then the time we extracted should be the fundamental limit. But until you measure it, you have no idea. And that's exactly the point. What I mean, there's so much still to find out. I mean, what is the damping of the
theoretical limit would be milliseconds, if I remember correctly? Or?
The theoretical limit for in this system is actually that the coherence time is twice as the relaxation time. So the relaxation time for electron spins at 1.5 Tesla as a second. So, but I don't believe that's the whole story. I think there's still a lot of interactions which are not discovered yet.
More questions? Yes.
I have one. I try to imagine how experimentally this looks like.
Yeah.
So you say that these quantum dots are buried, right?
They are buried in the chip basically.
Exactly, and you're working with one of them at a time.
Yes.
What is the typical output power that you can monitor
of quantum dots?
Yeah.
I think that would be 10 to watts.
10 to watts.
Yeah.
Okay. So is the emission directional?
No.
So how do you monitor output?
So the thing is,
because these are just few photons, right?
Yeah. So the thing is that I'm going to increase this. There. So the thing is, what you actually detect is not really the photons here. You detect the homodyne signal between the quantum dot and the laser. So in the end, what you end up with is the delta T is a term of the electric field of the laser, and then because you square the influence of laser and quantum dot, you get twice the electric field of the laser plus the oscillating dipole field of the quantum dot. So without this term here, there would be no way to measure this.
Okay.
So it's only due to this homodyne.
So it's a kind of indirect detection, homodyne detection.
Well, it's direct. But it's using this homodyne here. So.
Okay. And my second question was, if I understand you well, you have to work at very low temperatures.
4 Kelvin.
So, sorry?
4 Kelvin.
4 Kelvin.
Yeah.
Okay.
Yeah. So.
Sorry, because I heard about liquid helium, so I thought this was below 7 Ks.
No, this is all done in liquid helium. So here.
Liquid helium. Okay, sorry.
So that's basically all immersed in this liquid helium reservoir, and that's why it's so crucial to have this isolated system, because you have to refill this helium and everything. And to imagine to observe an object down here, 2 meters away, just from these fibers, you use the excitation to collect for 10 weeks. While I mean, the system now is so stable that you can actually shake this whole thing, and we don't lose this tiny object. So.
And just by curiosity, how big is this? Is it 1 meter high? Or?
So this is, I would say, 160, 180,
okay.
Roughly. This is 150, so this goes all the way down here. Usually there's a magnet around it here, so it's quite a microscopic thing to control the tiny object.
Thank you. And it's good for a quantum computer.
Yeah, it's perfect.
Just ask me, maybe I missed something, but you were mentioning when you apply the field, you have 2 lambda scheme in their problem.
Yeah.
But then, how does this enter into the description of the system?
They are just so far tuned in energy due to the Siemens splitting that we push them on. So that's I mean, the most interesting experiment for the future is, or one of the most interesting, is to map this the coherence time of the whole spin depending on the external magnetic field. So that this what you're talking about will exactly limit this experiment, because at some point the states will overlap, and then well at least the theory will become more tricky.
Okay, so let's take that in again. And